Lecture 6. This is the second and final lecture on the damped harmonic motion chapter, and in this lecture we will look at several problems before concluding with a brief treatment of logarithmic decrement and energy dissipation in damped harmonic motion. Okay, so exercise 1. We've got to consider that block spring dashpot arrangement, similar to the ones that we looked at in the previous lecture, just with a dashpot on the other side. Not that that would have any effect. Dashpot, as long as it is in the direction of movement or parallel to it, it's just going to give you a force in opposite direction to the velocity, no matter if it's to the left or to the right of it. Okay, so that won't change things. It just makes the diagram smaller. Okay, and we've got to find the displacement function. Okay, now before we do the problem, let's just quickly talk about how you approach these problems in as much as finding the differential equation if asked from first principles. In other words, we've got to put in all the forces and use Newton's second law. What changes is, well, basically nothing. You just have the damping force that gets added. The rest is pretty much exactly the same. So if, say, you add this horizontal arrangement, then you would go about it the same way. You'd say, let's say that be with the x direction, and I don't know, at some point you've got xt, which is just a displacement function, so you would say that that is my displacement function from equilibrium, and you would say, all right, okay, so I've got my spring there, and I've got a dashpot, which is indicated like this in a diagram. And so this thing is K and this thing is B, and then the rest of the approach would be the same. I mean, you would have your weight. So strictly speaking, we'd have to put in a y-axis as well, and of course that's just going to be balanced out by the normal force, and we still have our spring force. And now the only thing that's different is we get a damping force, but that is all that's different. The damper does not in any other way affect how you approach this. It's just an additional force. That's really it. Apart from that, it's really exactly the same to the simple harmonic case, where you have to derive from first principles a particular differential equation. So you would do the same thing. Well, let's write it out for you, just to be, for the sake of completeness. You would start with the same way, net force equal to mass times acceleration, and now you would say that that is a spring force, and the damping force, and the weight, and the normal force equal to mass times the acceleration, which is just going to be x is the second derivative times unit vector in the x direction, and this will just be minus k, let's say x I, and this will be minus b x derivative I, and this will just be y I chose up, not that it matters. Okay, okay, same old story, equal to mx I, okay, so just the same essentially as what we did in the previous lecture. Okay, and it doesn't change even if you've got a vertical arrangement. Let's say you've got a little spring, and you've got your mass, and you've got your dashpot, and you've got ground there, let's say. Well, the dashpot could be at the top, it doesn't matter. And let's say, I don't know, downwards, you choose a positive y direction, then I mean it would still work the same. You'd, let's say that is my vertical displacement, and let's say the thing is already stretched by distance d when it is at equilibrium. And remember, at equilibrium, now if you want to find this d, you're concerned with what the arrangement is at equilibrium. And at equilibrium, when the whole story is standing still, then there is no damping force. So finding d is not affected at all by the presence of the damper. You're still going to get that kd is equal to mg. Otherwise it's really exactly the same. You have the weight, and you've got the damping force here, and you've got the spring force over here, and then it's the same. F net equal to mass times acceleration, and now this is the spring force plus the damping force plus the weight, and this like that. This is minus k, same y plus d as we explained, j. And damping force is just minus k y dot j, and then this is plus mgj equal to my open j, but this minus kd and this mg term will just cancel and you're left with the same kind of differential equation. Okay, so the presence of the dashpot doesn't really change much at all, in as much as deriving some differential equation from first principles. Okay, so not much changes in that sense. Okay, but the question did not ask for this, so we don't have to worry about it. Okay, so we can go straight to the question and let's see again. Okay, we're given the mass and the spring constant and three possible damping constants. So let's do the first one, 1a. Okay. It's bad manners to introduce or just use functions without saying what they are. So let's call x of t the horizontal displacement from equilibrium. Displacement from equilibrium, and please don't abbreviate yourself in answers. Okay, and now we can start off by saying, because this is a setup that we recognize and that we studied carefully, we can start off by saying that it satisfies that differential equation that we have derived and are able to derive ourselves if needed. Okay, and we're given some initial conditions that initially it's pulled by 0.5. Okay, so in other words, I'm making the positive x direction the direction in which it is pulled initially, and it is then released, so the initial velocity is 0. Okay, so 0.5 meter. And for easy reference, let's include the mass. It is 20 kilograms and k is 2000 Newton per meter, and b in this question is 500 Newton per meter per second, or Newton second meter power minus 1. Okay, good, like that. All right, so for easy reference, good. Now, this is where I can start. Now I've got to ask, what is the solution? Now this we studied extensively. We know that it depends on those checks. We can compare p squared to omega squared, or we can compare b squared to 4km. You can choose whichever one you want. Let's do b squared and compare to 4km. So b is 500, so this will be 25 and 4 zeros, so 250,000. And 4km is 4k is 8,000 times m is 1,660,000. Okay, so thus b squared is greater than 4km, so thus it is over damped. And thus we know what the general solution is. Now we used to check b squared versus 4km. Nothing stops you from doing the p and omega one. We're going to use p and omega anyway, so because it's just a simpler notation. So let's write down what they are. We'll use them in a couple of seconds. So b is there's 500 divided by 40 kilograms, so that's 50 over 4, so that's, well, let's leave that as 25 over 2. And omega, the natural frequency of the associated simple harmonic motion, good, 2000 over 20, so that's 100. Squared to 100 is 10. Okay, so yeah, the values are chosen, so it works out nicely. Okay, so, right. We're going to use that, so we calculated them. All right, now, we see from this is overdamped, so we also know that the general solution is therefore x of t equal to a e to the lambda 1t plus b e to the lambda 2t. And lambda 1 you can calculate is equal to minus b minus the square root of b squared minus omega squared, and that you can calculate with well, I mean, it's fun. It's not a bad idea. Sometimes see if you can work these things out by hand. Let's see if we can do that. If you don't want, then skip ahead. All right, or just use a calculator. But let's see for the fun if we can do that. Okay, so we've got minus 25 over 2 minus, and then here we've got the square root of 25 squared over 4 and minus 100. Okay, so let's look at this thing. So I can take out the 1 over 4. So what's that? That's minus 12.5, if that's helpful. I can take out the 1 over 4, so then I have a half left. And then I've got the square root of 25 squared minus 100, minus 400. Okay, so this can be 25 squared minus 400. Okay, 25 squared I can write as, let's say, 100 over 4 times 100 over 4. So then this will become 10,000 over 16, and here I had left 400, so now this would become 400 times 16 over 16. Okay, and what do we have here? 400 times the 16 is 2 squared times 2 to the 4 times 100, so that's 2 to the 6 times 100, so that is 6,400. So we're left here with minus 2.5 minus a half times square root of all of this over 16. So in other words, that's a 4. I can take out a 4, so it's 1 over 8. Okay, and then what do we have here? 10,000, so 3,600. Okay, it's perhaps a bit unfair that it works out this well. So that is 60. 1 over 8 minus 60 over minus 1. Okay, all right. So what is that? Okay, so 60 over 8 is, it's 30 over 4. It's 15. No, let's not get ahead of ourselves. 30 over 4. So that is 15 over 2. So 7.5. So minus 12.5 minus 7. Yeah, okay. So it works out very nice. Minus 20. That's going to be the one term. So this one will work out to be minus 20. And lambda 2, then it's going to be minus p plus square root of p squared minus omega squared. So now it is just going to be plus that, so it's minus 12.5 plus 7.5, so minus 5. Good. All right, so sometimes if you're bored, it's a good idea. It's in any way a good idea to see how far you can get without a calculator, just to help you develop a feel for what answers should be. It's a great way to catch yourself mistakes. Most mistakes that I catch myself in is when I get an answer and it doesn't make sense. It shouldn't be that large, it shouldn't be that small, or it shouldn't be positive or it shouldn't be negative. And it's difficult to develop that kind of sense with these problems if you immediately do everything by calculator. So try to manage sometimes a bit without the calculator. Okay. All right. Okay, so that was a bit of a detour, but okay. So welcome back for those who skipped ahead. E to the minus 20t plus b e to the minus 5t. All right. Okay. Good, so we have that. Now I want to find a and b, so now I just use my initial conditions. So let's substitute that initial conditions. So x of 0 is a plus b, and that should work out as a half, 0.5. Now the derivative is just minus 20a times e to the minus 20t minus 5b e to the minus 5t. And so therefore the derivative at 0 is minus 20a minus 5b, and this should be 0. Correct? Good. All right, now let's call that 1 and we call this 2. And now we are going to substitute 1 into 2. Okay, so when we do that, we get minus 20, and a is therefore in terms of b, 0.5 minus b minus 5b equal to 0. So this is minus 10 plus 20b minus 5b equal to 0. So in other words, this is, what's this? This is minus 15b. Okay, so I've got minus 15b, so I take the right, so 15b is equal to 10. So b is equal to 2 over 3. Okay, and a then is a half minus 2/3, that is 1 over 6. Good, all right, and we're done. Well, kind of almost. We have to write down what the actual final solution is. There's a nice spot for it. So the final solution, now you can go and plot a graph for it using Sage Math or whatever else you use. Minus 20t plus 2 over 3 e to the minus 5t. Good, and there's the final answer. Okay, so for b, we just have a different damping constant. So let's see what effect that does. All right, so we already wrote all of this. So we assume that we consider it as we're just continuing. So I'm not going to write all of this down again. So we'll just write that we've got a new b now. So b is equal to 400 newtons per meter per second. And let's see. Okay, so let's do the same check. So b squared will now be 1660,000. And of course 4 km will stay the same. Well, equal to 4 km. Okay, so thus this is critically damped. All right, the case that people are often interested in achieving. Okay, and again, we're going to be using the p and the omega term. So let's see where I write it down. So p is equal to b over 2m. So that'll change slightly now. So b is, so it's 400 over 40 kilograms. So 10. And omega s squared of k over m also remains 10. Okay, right. So now that we know what the general solution is, because we've studied this case extensively, generally the general solution is, the general solution is, as we've seen, x equal to e to the minus pt a plus bt. And we've now calculated some of these things, so we know that's e to the minus 10t a plus bt. Right, now the initial conditions are the same, so let's substitute them. Initial conditions, x of 0 is 0.5 and x of 0 is therefore just equal to a. All right, so it works out very nicely. All right, so we already know what a is. Now for the derivative, let's differentiate first. Okay, so all right, so we can, okay, but let's just straight differentiate it. Okay, so in other words, so that would be product rule. So we get minus 10 e to the minus 10t times a plus bt plus b e to the minus 10t. Okay, now I don't know if there's any simplification here. Doesn't look like it. All right, so let's substitute 0, and that should work out to 0. So what do we have here? Let's see. Okay, so we have minus 10, a minus 10a plus b, and that should be equal to 0. So in other words, b is equal to 10a, but a is 0.5, so b is equal to 5. All right, so this was very easy. So the general solution is x of t is equal to minus 10t, 0.5 plus 5t. Okay, all right, so these are simple initial conditions. Of course, initial conditions could be a little bit different with other problems. Perhaps it is given initial velocity, you hit it with a hammer or whatever, and then perhaps this is not a nice 0 value. But, I mean, still, it would be easy to solve. Okay. And right for C, we have to consider the case where b is much smaller, so we can already expect that this should be, well, we know based on b and a that this should now be the underdamped case. Okay, so similar to b, let's just write down what the new value is, 100 newtons per meter per second. And okay, so we do the same check. P squared is now 10,000, which is far less than 4 km, which we calculated this already know is 160,000. So, okay, we need some space here, so let's write here. So this is lightly damped or underdamped. I think underdamped is the better term. So that's lightly damped. Okay, so now we know, based on what we've already seen, based on the investigation that we've done, that the general solution in this case will now be x equal to c e to the minus pt cosine of omega prime t plus some phi. Now, some of these terms we can calculate. So let's do that over here. We're going to use a p. All right, so what's p? It's p over 2m. P over 2m. What is p now? It's 100. And 2m, so it's 100 over 40. So that is 2.5, or 5 over 2. Well, let's just leave it as 5 over 2. Okay, now, and remember, this is omega prime. It's not exactly the same as omega, though it will be very close if b is very small. So omega squared minus p squared. Okay, so omega squared, we already know that that is 100. So it's 100 minus this squared, minus 5 over 2 squared. Okay, now, for the fun of it, let's see if we can get an idea of what that value might be. Okay, now, okay, so again, skip ahead if you want to just use calculator. All right, so let's see. We've got here 100 minus, this is effectively 2.5 squared. All right, so let's see, what is this? Okay, so how can I write this? I can write this as 100 minus 10 over 4 squared, so that is going to be 100 minus 100 over 16, so 1,600 over, so 1,500 over 16, and it's the square root of this whole story, and that is 750 over 8, 375 over 4. Okay, so the whole thing reduces to the square root of 375 over 2. Yeah, okay, well that's simple enough that I can just write that each time and tag it along. All right, so we can delay the calculator a little while still. So let's just call it 375 over 2. I don't believe that is a square. I don't, no, it isn't. Okay. Okay, so let's see. All right, so we've got something. Okay, so let's write that. So x is then equal to c e to the, let's, as it's always vertical real estate, let's write it rather as minus 2.5t cosine of, okay, let's use the vertical real estate here, a half square root 375t plus phi. Okay, excellent. All right, now, so what do I not know? I don't know c, I don't know phi. So similar to the simple harmonic motion cases, we just have to substitute initial conditions. Okay, so let's do that. All right, so x of 0, that is just going to be c cosine phi, and that should be 0.5. All right, so I'm definitely going to be using this again. Let's call that 1. Well, perhaps I shouldn't call it 1. I forgot that we used 1 in the previous answers as well, but okay, never mind. Okay, right, so now we want the derivative at 0. All right, so let's calculate the derivative. So x prime of t, of x dot of t. Okay, so now we just have to differentiate this story. Okay, so this is minus 2.5 c e to the minus 2.5 t cosine of a half plus phi, and here you just have to keep track and be careful that you don't make any mistakes. Okay, and then it's going to be minus of square root of 375 c e to the minus 2.5 t sine of square root 375 t plus phi. Okay. Okay, all right. And what do we want? What do we know? Is this thing's value at 0, which is going to be what? It's going to be, that's just 1. Okay, so let's see, we get minus 2.5 c cosine phi minus this half square root of 375 c sine of phi, which must be equal to 0. Okay, now I can get rid of the c. I can divide out with c on both sides because I know c is not going to be 0. For c, 0 means that x is just constant 0, which I know is not going to be the case here. I don't even know what the solution needs to look like in any detail. I mean, for starters, it starts off at 0.5 meters, so it's not the case that x is exactly 0. So c is non-zero, so I can divide by it. All right. So if I do, all right, let's do that carefully. All right, let's. How shall we write this? Okay. Let's lightly, it's a pencil already or whatever. So let's just say, see, we can divide out. And now I can plus the sign on both sides. So I can, no, I'm going to divide by the cos. Oh, okay. Okay, if you're not sure, rather not risk it. I just want to see which way around I'm going to divide here to make it most obvious. So I want cosine on the, well, on the right. Yeah, okay. Let's make it plus 2.5 cosine phi is equal to minus a half square root 375 sine phi. Okay, good. Okay, so I'm just divide by cosine on both sides and then divide this out. So what I'm left with is tan of phi is equal to, or phi is equal to, I divide by that. So what do I get? So it's going to be 5 divided by half is hard, so it could be minus 5 over square root of 375. Okay, good. So phi is therefore equal to, okay, and now I'll relent. I'll use a calculator for this. Minus 5 divided by square root of 375. Okay, so we're going to get minus 0.25 plus n times phi. Okay, yeah, pencil. Which of course makes sense because you know what the tan graph looks like. So we found that value now, but plus multiples of pi. We have it on all sides. Okay. All right. Now we similarly going to simple harmonic case. We're going to try to get the value for which c is positive, not a mathematical imperative. It's just nicer that way. Because c can be then directly interpreted with the correct sign as the starting amplitude. All right, so let's see. Let's try phi equal to minus 0.25 in 1. So then that means c is equal to 0.5 divided by cosine of 0.25, which is the same as minus 2.55. That's fine. 0.51. No, 0.52. Good. All right, and that's it. So thus x of t is equal to, what did we get? 0.52, where's all the terms? E to the minus 2.5 t cosine of, now I've got, let's write like this, 375 over 2t plus, oh no, minus 0.25. And there we have it. That's the final answer. Good. All right. And that's it for question 1. Okay, so now we get to a very interesting problem. We're looking here at an RLC circuit, a resistor, an inductor, and a capacitor. It's an oscillator circuit if the resistance R is low enough, meaning the current continuously changes direction at a certain frequency. And now the question asks something strange. For what ohm range of the resistor of the resistance in this circuit is the above circuit an oscillator circuit for those values of the capacitance and inductance, 4.5 microfarads and 350 millihenries. Okay, so this is a great question. What's going on here? We've looked at at LC circuits before, where we use Kirchhoff loop rule to define the differential equation, and we saw that what is predicted is we'll see simple harmonic motion for the charge Q on the capacitor. In other words, discharging a capacitor through an inductor simply causes the charge to continuously of the charge of on the capacitors to switch polarity continuously in a simple harmonic motion fashion. But of course, there is going to be resistance, so we necessarily have a resistor. And now we get all right. So things are a bit unclear. So let's do the same thing that we did when we looked at LC circuits and find a differential equation. So let's see. What do we have here? Okay, so let's quickly rewrite the diagram. All right, so I've got my capacitor that is charged now. I've got the resistance in the circuit indicated by resistor R. Okay, and I've got an inductor with inductance L, and this is C. Okay, and what we have to remember is we've got to remember that. Okay, well, we'll see when we use Kirchhoff loop rule. What we have got to remember for the capacitor is that the charge on it Q is related to the capacitance and the voltage across the plate by CV. All right, that's all we have to remember. Okay, and now what's going to happen if I perhaps here's a switch here that I close at t equal to 0, then current is going to flow in this direction, conventional current. Capacitor is going to try to discharge. Okay, now let's use Kirchhoff loop rule. So from there to there, I'm going to have, now let's see, where should we do this? Let's do it over here. Okay, so this is Kirchhoff, I hope I'm spelling this correctly, Kirchhoff loop rule. Let's see what that tells us. Okay, starting from here to here, a low to high potential, so that is going to be the voltage from there to there is going to be 1 over CQ. And then here we're going to get minus I R, and here we're going to get, just like we did when we looked at Kirchhoff loop rule in, I think it was the first lecture, in the second part of the first lecture. Here we're going to get minus L di dt equal to 0. Now, when we looked at it back then in the first lecture, we used the fact that the current I is equal to the rate of change of the charge on the capacitor. Quite right, but there the capacitor was charging as we set up the diagram. Here, the capacitor is going to be discharging. Now ask yourself, if this thing is discharging, this capacitor, then the rate of change of Q, the charge on it, is going to be negative. So the current going around, the conventional current in this case, will be minus this. So let's use that. So we have 1 over C Q here plus R times dq dt plus L times second derivative Q dt squared equal to 0. And let's rearrange this a little bit. So we have L second derivative Q dt squared, and let's put that, plus R dq dt plus 1 over C Q equal to 0. And hopefully this looks familiar to you. Let's write down what we saw that was similar to this. What we saw that was similar to this was mass times second derivative of displacement plus b derivative of x with respect to t plus k x equal to 0. This is what we saw. So lo and behold, even though we spend a lot of time looking at mass spring dashpot systems, what we were really investigating was actually a kind of differential equation. So we were not restricting ourselves to those kind of mechanical mass spring dashpot systems. We were in effect investigating whatever system has this kind of differential equation. And here we already have discovered one outside of mechanical block spring systems. And this one we have analyzed completely, utterly and completely inside out. We've analyzed this, which means we know exactly what's going to go on here. And what is going to go on here? This is either going to represent overdamped, so that would just mean that the charge Q, the value Q, will just go down to 0, so the capacitor would slowly discharge, or it could be critically damped, and then the capacitor will discharge very quickly, or it could be underdamped, and then the capacitor's charge Q will then flip polarity, but not by the same amount each time. The amplitude of those oscillations will take down, so the polarity of the charge on the capacitor plates will change, but they will lose a little bit of charge each time. Okay, so we can deduce that to come to those conclusions because we've analyzed this differential equation in full. And I know which case is going to happen. So what case are we interested in? We're interested in the oscillating case, right? That's what we are interested in. And how does the question stated? In what ohm range should R be so that it is an oscillator circuit? So oscillator circuit presumably oscillates, and we know it with analogy, with direct analogy with this. There's only going to be oscillation when it is underdamped, and I know that underdamped is when what is true. That is when B squared is less than 4km. So that's what I know. So therefore I know here are the oscillations will be when, right, now let's see, B squared less than 4km. All right, so what is B here? That is R. So R squared, so you see here the resistor plays the role of the damper here, which makes sense if you think about it. Should be less than 4. And what's K here? C, okay, C and M is minus 4 L over C, is it? Let's just check that. R squared should be less than 4. K is 1 over C, and M here is L. Yeah, like that. So R squared has to be less than 4L over C. And let's calculate that. What is that? So R should be less than square root of 4 times. All right, now let's substitute the values. Let's see, what are they? L is equal to 350 times 10 to the minus 3 henries. And the capacitance is pretty standard value of 4.5 times 10 to the, micro, minus 6 farad. All right. And it's way too late at night to try and work that out. So let's just say square root of 4.35 times 10 to the minus 3 divided by, okay, let's just change that to 3, right? Divided by 4.5, okay. All right, yeah, okay. So R should be less than 31 ohms. Okay. So if R is less than 31 ohms, with R playing the role of the damper, in the mass spring dashpot system, which we completely analyzed, then there will be oscillations. The charge Q will then flip polarity continuously, but at a decreasing rate. So each time the charge will reduce a little bit. Okay, where the charge here plays the role of the displacement in the mass block spring system. Okay, so this is a very significant problem. It's worth noting carefully what happened here. We spent a lot of time looking at mass spring dashpot systems, but really what we were investigating was a kind of differential equation. And then that analysis immediately carries over when we encounter it again. We just have to see what all the corresponding terms are. Good. Okay, so for the second to last concept in this chapter, we're going to look at the logarithmic decrement. Now, since critical damping is something that is often desirable, denoting the quickest way close back to equilibrium when disturbed, there needs to be some way to tell how close or how far a system is to critical damping, some measure of it. And this we define with the damping ratio, which very directly states it. Logarithmic decrement ultimately will be a way to get this damping ratio. Okay, so look at the definition. It's zeta, denoted by zeta, and it is defined as the damping constant of your system that you are looking at divided by what the damping constant would have to be for the system to be critically damped. So what you have over what you want. The damping constant of your system divided by what the damping constant would have to be for the system to be critically damped. So therefore, if zeta is less than 1, then obviously the system is underdamped. B is less than it needs to be a critically damped system. And if zeta is 1, then it is obviously damped, critically damped. And if zeta is greater than 1, if B is more than it needs to be for it to be critically damped, then it is overdamped. Good. All right. So zeta is what will tell us how close we are to critical damping. We will obviously be able to tell from the oscillations. If there are oscillations, then we know that it is zeta is less than 1, and if there are no oscillations, then we know it is greater or equal to 1. But what we really would like to know is how close it is to 1. How close what we're looking at is how close what we are looking at is to critical damping. Now, okay, so that's just repeating what I say. Now, you can think a bit about how to write zeta in a different way, because what we're now trying to see is how we're going to actually find zeta. So the obvious, or the intuition, or the instinct rather, the instinct would be to let's see if we can write it in a different form that is usable. And this, we can indulge in that a little bit and see what we get, but it's going down the wrong path, as we will now explain. We already know this, so refer to the previous lecture. This follows directly from it, where beta squared is equal to 4 km, then it's critically damped, so that the damping constant for critical damping would therefore have to be 2 squared root of km. And then you can see that zeta can be written in this form, P over omega. Now, well, this isn't really that helpful. If I have all of the constants, then I have B in particular, and I can easily determine how close I am to the critical damping constant. The point here is, what if I don't have any of that? What if I'm just looking at a graph showing the oscillations of some oscillating system? I don't have an M value, I don't have a B value, I don't have a K value. I'm just looking at a graph of oscillations. How on earth am I going to determine zeta then? And this is where the logarithmic decrement comes in. So what we define the logarithmic decrement as is simply the natural logarithm of the ratio of two maxima a period t apart. So if you want to calculate it, all that you do is you go to one peak in the oscillations, and let's suppose that the vertical axis is x and the horizontal axis is t. So then you just find one peak, see how high it is, what is its x value, then go to the next peak, see what its x value is, divide those two, and calculate the natural logarithm of it. And then you have the logarithmic decrement. If we define it very precisely, then this is what we have. Delta here is used to indicate logarithmic decrement. It's a natural logarithm of the displacement function t divided by t plus nt. Okay, so what is the n's purpose here? What I just explained here is when n is 1, when we just look at the next peak, but depending on the graph that might be difficult to do. Perhaps the oscillations are very fast and it's difficult to go from one peak to the next and get an accurate value. Perhaps you can perhaps you have one peak and you can read off its x value, but the next peak is a little bit difficult to read. But about 5 peaks later, you can read off the x value pretty clearly again. So then you can do that. So then you go to the x value 5 peaks further, and then n is 5. So then you just have to divide it by 5. So you can go from one peak to the next, or one peak to 13 peaks later, and read of that x value, but then you've got to divide by 13. Okay, and as you can see here, because t is the period, these two terms will be the same. So all that we're left with is 1 over n ln e npt, so p times the period. Okay, but this is not really important. This is not what you're going to be using to calculate it. This is just showing what it works out as. What you'll be interested in is this. So again, to calculate the logarithmic decrement, if x is your vertical axis, find one peak, read off the x value of that peak, find the next readable peak, perhaps it's 7 peaks further, write down that x value, so you're dividing those two x values that you just got, calculate the natural logarithm of it, and divide by 7. Or if it's from one peak to the next, then n is 1. Okay. And then if you can calculate that logarithmic decrement, then you can find zeta with this formula. Now, I don't want to go through the derivation of this. I think that is going a little bit too much into niche detail, but you're certainly welcome to see if you can show that zeta is indeed given by that formula. But the point here is zeta is a function that very directly tells us how close our system is to being in the pleasurable or desirable critically damped state. And it's something I can work out without knowing any of the constants. I just need the graph. I don't even need to know what the units of the x-axis is. I just need to know the relative height of the peaks. And I can just read this off and calculate it, plug it in here, and I get my zeta, my damping ratio. And finally, for this chapter, let's look at energy dissipation. We've seen with all of the possible cases where there's a damping force involved, the system eventually comes to a standstill. So it loses energy, and let's see if we can work out how much that it is losing. Now we know that we have got the formula for the total mechanical energy. We derived this previously, and it is in this form. So we can now see, we can now go ahead and calculate the derivative of this and see what we get. So let's just differentiate it. No funny business, d dt. And we go through the motions, take out the derivative of x as a common factor, and I get this expression. And I know for the systems that we are currently investigating that this is equal to minus bx derivative, straight from the differential equation for these damped simple harmonic cases. In other words, this I recognize as the damping force. So therefore, the rate at which we are losing energy is given by the velocity times that damping force. Okay, and what is this? If you want to interpret it, let's see in terms of, or perhaps you recognize it already from first year, but let's look at the units. Meters per second, and force in newtons, that is Newton meters per second, joule per second, watts. So that works out at 2 watts, great, which is what it should be. So we're losing energy at that many watts. So that is work done against a rate of work done against a force, which you can go and revise from first year. And it's exactly as we would expect. The damping force is sucking mechanical energy out of the system. Piston is getting hotter, or in RLC circuit, the resistor is getting hotter. Okay. And now finally, let's derive a nice little approximation for the energy in these damped cases. Now we saw in the undamped simple harmonic motion oscillators, the simple harmonic motion case, that the total energy is given by this expression, half kc squared, where c is simply the amplitude of the oscillations. But we know that we can have in the damped case also oscillations. The only difference compared to the simple harmonic motion case is, well, as we saw in that animation, the last animation in the previous lecture, the frequencies can be a little bit different. That's a minor thing to notice. More obvious is that the amplitudes are decreasing. So it's still oscillations, just at a decreasing amplitude. So then we get this idea. Perhaps we can just use the same expression, this exact same expression. We just replace the amplitude with the amplitude in the damped case, in the damped oscillations case, in the underdamped case. And there it is, with the original amplitude c multiplied by this term. This is how fast the amplitude is decreasing. So that's the idea, and that does work. The energy is approximately equal to half k, just except we don't have a constant amplitude, we've got a changing amplitude. So we can use this expression as an approximation of the total mechanical energy of the oscillations in the damped case. But it is an approximation. It doesn't work out exactly to this. It is going to be affected by the value of B. But if you want to get a quick indication of the mechanical energy, then you can use this expression. But be wary that it is an approximation, but it will be a pretty good approximation the smaller B is. Okay, and that is it for the chapter on damped harmonic motion.